Money management begins with savings. Personal savings are becoming more and more crucial as employer-sponsored retirement plans and Social Security benefits dwindle. In terms of saving, ideally you would like to retire and enjoy the same standard of living. But what many people don't account for is the standard increase in the cost of living, age-related health expenses, and so forth. Thus, the need to begin saving now is crucial for ease of mind come retirement. We saw an example of this in our previous lecture. A box of macaroni and cheese cost 25 cents in 1976. Accounting just for inflation, what should the price be in 2005? When we are in a state of inflation, every dollar buys a smaller percentage of a good or service. Changes in actual prices are not meaningful unless we compare them to the overall rate of inflation, which is measured by the Consumer Price Index. In this example, we compare the ratio of the CPI in 2005 to that of 1976. The CPI in 2005 was 195.3. The CPI in 1976 was 56.9. Calculating this ratio, we can see that the average cost of goods and services in 2005 is approximately 3.43 times as expensive as they were in 1976. This means that our 25-cent box of macaroni and cheese is going to cost roughly 86 cents in terms of the 2005 dollars. So the question becomes, how can one prepare for the eventual increase in the overall cost of living? The solution comes in the form of savings for the future. Paying yourself first from your disposable or discretionary income is key. Disposable income is income that you have remaining after all living expenses have been paid, such as rent, utilities, transportation, food, etc. By paying yourself first or working a savings category into your monthly budget, you are developing a savings habit and preparing yourself for the future. How much should you have in your savings account? Experts recommend at least 6 to 9 months of expenses be kept in a savings account. The purpose of this is for times of crisis, losing a job, being forced to find a new source of income, unexpected or major breakdowns for vehicles, appliance, or home repair that may or may not be covered by insurance. The downside, if you can call it one, is that unfortunately these days the interest earned has not kept pace with the rise of inflation. This means that other sources of income will be required to maintain the same standard of living you currently enjoy. We will talk more about other investment types in the near future. Before we take a look at different types of savings accounts, let's take a look at a few key terms. Interest is the amount of money that we get paid for lending or investing money, or that we pay for borrowing money. When we deposit money into a savings institution, the institution pays us interest for its use. When we borrow money, interest is the price we pay for the privilege of using money until we repay it. The amount of money that we deposit or borrow is called the principal. The interest rate, which is given as a percentage, determines how much interest we will earn or be charged. Simple interest is interest paid only on the original investment, or the original borrowed amount. Simple interest is usually used for loans lasting less than 1 year. Simple interest is interest charged on the entire principal for the entire length of the loan. It is found using the following formula: I equal to PRT. I refers to the total interest earned or charged. P is your principal, the amount borrowed or the amount placed into the account. R is your interest rate. T refers to the length of the loan in some number of years. Compound interest is interest paid both on the original investment and on all interest that has been added to that original investment. The added bonus of compound interest is that for every calculation of interest, i.e. compounding, the principal is changed to include the previous amount and the interest earned thus far. You are earning interest on interest. Or if you're borrowing money, you're being charged interest on interest. Compound interest can be found using the following formula. Let's identify the key variables in the compound interest formula. This is also referred to as the lump sum formula. A stands for your accumulated balance at the end of the term, or the future value of the account. P is your principal, the original investment or deposit, also referred to as the present value. APR is your interest rate, or annual percentage rate. N is the number of times the interest is calculated or compounded in a single year. Y is the number of years, or the length of the loan. Pay close attention to the variable y. It must always be represented or expressed in terms of years. If I only hold an account for 6 months, the variable y would be 1/2 or 0.5. Let's take a look at the comparison. Suppose you invest $1,000 into an account earning an annual percentage rate of 10% for 50 years. Situations involving simple interest are fairly rare and usually occur when money is loaned or borrowed over a very short period of time. As we will see in the following example, interest earned on an account with compounding is always at least as much as that earned from simple interest alone. If the money is invested for a short time, simple interest can be used as a rough estimate. The table on the following page compares simple interest and annual compounding over a 50-year span. In both cases, we begin with a principal of 1,000 and an annual percentage rate of 10%. The end of the first year, the interest earned in simple interest would be $100, or 10% of the original balance, which is $1,000. So therefore, at the end of year 1, our balance in the account would be $1,100. Since simple interest is calculated only on the original balance, the interest earned every single year is going to be $100, or 10% of the original investment, the original $1,000. We see that the balance increases, but every year the interest earned is only $100. Therefore, at the end of 50 years, the balance in the account due to simple interest would be $6,000. Now take a look at compound interest. Again, at the end of year 1, the interest earned is 10% of the original balance, or the original principal of $1,000. So the ending balance is $1,100. Here's where compounding begins to take place. At the end of year 2, here's where compounding begins to take place. 10% is still earned, but that 10% is going to be based upon the ending balance of year 1, meaning we are going to earn interest on $1,100 instead of the original investment of $1,000. So the interest earned at the end of year 2 would be 10% of $1,100, which would be $110, leaving me with a balance at the end of year 2 of $1,210. As we can see, the interest begins to grow in the compound interest equation. Notice that the balance for simple interest is growing by the same amount, $100 each year, because the interest on the account is based on the original principal, or the original $1,000. Compare that to the balance for that of compound interest, which is growing by the same percent, 10% each year. Therefore, compound interest is an example of exponential growth. If we were to graph the yearly balances of the previous problem, we can see how early on in the process simple and compound interest are relatively similar. However, once compounding takes hold, the difference in the graphs are widely apparent. This is why it is so important to begin saving early in life to take advantage of the effects of compounding. Notice from the graph, the effects of compounding do not take big effect until around year 10 and beyond. Let's take a look at some examples of simple and compound interest. When trying these problems, it is important to look for key phrases to guide you in selecting which formula to use. Suppose you deposit $1,500 into a CD, paying an annual interest rate of 4.3% compounded quarterly. What is the balance after 6 years when the CD matures? The key phrase, compounded quarterly, tells you that interest is being calculated or compounded 4 times per year. So that means we want to use the compound interest formula. So substituting all of our appropriate values in, we see that the accumulated balance, or the balance at the end of those 6 years, can be calculated or found by taking the principal of $1,500 and multiplying it by 1 plus the annual percentage rate divided by 4, all raised to the number of compounds 4 quarterly times the number of years 6. Follow the order of operations in order to simplify the right-hand side to find the accumulated balance, or the balance at the end of those 6 years. The future value, or the balance at the end of those 6 years, would be $1,938.84. Another question would be to find the interest earned on that account. The interest earned on that account was $438.84. Remember, the original deposit of $1,500 was our own money. Therefore, the difference between the accumulated balance and the principal must be the interest earned on that account. Let's take a look at another example. You deposit $5,000 in a bank account that pays an APR of 3% and compounds interest monthly. How much will you have at the end of 5 years? Compare this amount to the amount you'd have if interest were paid only once each year. Pause the video here and try this example on your own before moving to the solution on the next slide. Again, we want to look for key phrases to indicate what type of compounding is taking place. We see that in the first example, we are compounding interest monthly, and in our comparison, we are compounding every single year. Let's take a look at monthly compounding first. Again, monthly compounding, or compounding 12 times per year, indicates that we're going to be dealing with compound interest. We're looking to find the accumulated balance, or the future value A. We know that the principal is the original $5,000 that we invested or deposited. Our annual percentage rate, or the interest rate that the bank is giving us, is 3%. We are compounding interest monthly, monthly meaning 12 times per year, over the course of 5 years. Follow the order of operations in order to simplify the right-hand side, or to find the accumulated balance. Take a look at yearly compounding. Again, yearly compounding meaning once every year. So again, we're going to be dealing with the compound interest formula. The principal remains exactly the same. It's the original $5,000 deposit. Interest rate is still 3%. This time, instead of compounding monthly or 12 times per year, we're compounding yearly or once per year. Still over the course of 5 years. Follow the order of operations to simplify the right-hand side to find the accumulated balance, or the future value of this account. We see that after 5 years of monthly compounding, the accumulated balance in the account is $5,808.08. After 5 years of yearly compounding, the accumulated balance on the account is $5,796.37. Monthly compounding earns you an additional $11.71.